This is a video presentation of Chapter 2, Section 1, Rational Numbers. And our objective here is to write rational numbers in equivalent forms. So what is a rational number? Well, luckily for us, the vocabulary words for this section start off by defining what a rational number is. A rational number is any number that can be written as a fraction n over d, where n and d are integers and d is not equal to 0. Any number that can be written as a fraction, n over d, where n and d are integers and d is not equal to 0. Now, of course, they've used n over d there because n and d are going to stand for numerator, which is the top part of a fraction, and d, which stands for denominator, which is the bottom part of a fraction. So all they're really saying is if you can write it as a fraction, which most things can be written as a fraction, that was what would make it a rational number. The ways, the exceptions, the ways it would not be a rational number would be, for instance, if it's a number that repeats forever in decimal form but does not have a pattern to it. We know that things that have a pattern to it can be written as a fraction. For instance, probably the best example is that 0.3 repeating that we've seen so many times over the years. Well, we know that's already 1/3. And you can check that on a calculator, do 1 divided by 3, and it will give you that 0.3 repeating with 3's all the way across the screen. Some other examples, and there are very few, square roots of negative numbers really can't be written as a fraction. That's kind of a whole different thing entirely. We really won't spend much time on that concept. Pi is also another thing that cannot be written as a fraction. Yes, it is true. Sometimes we approximate that as 22/7, but that's not actual value of pi. Notice they're saying there d cannot be equal to 0. Think about that. Think about what a fraction represents. If we go back to our basic understanding of fractions from elementary school, something like 1/3. Well, if we think of it in terms of, again, elementary school, let's say I have a pie and I have 3 pieces of that pie. All right. Well, the fraction 1/3 would imply that I've, let's say, eaten one of those 3 pieces of pie. So if we flip that and use that same idea but let the denominator equal 0, let's say that would be 2 over 0. And again, I can use any number I want on the numerator. It really doesn't matter. The fraction 2 out of 0 would mean I ate 2 pieces of pie, which sounds good in theory, but remember, the bottom number would mean that I have no pieces of pie. Well, I can't eat 2 pieces of pie if I didn't have any to begin with. Now, the fraction works fine the other way, though. If I wrote it as 0 over 2, again, using this pie as my example here, that would mean I ate no pieces of pie, but I had 2 to begin with. So having 0 in the numerator, although it's not really all that proper, is not an issue, but having 0 in the denominator is a serious issue, and that's why they're saying d cannot equal 0. And we've also got the definition of relatively prime. Relatively prime says 2 numbers are relatively prime if they have no common factors other than 1. 2 numbers are relatively prime if they have no common factors other than 1. So what you would want to be thinking about here is the idea of greatest common factor. And as you go through and use the approach of listing the factors, those lists of numbers that you're working with, generally 2 numbers, as I list the factors of those 2 numbers, the only number that would be on both lists would be a 1. And when that happens, those numbers are relatively prime. It does not mean that the numbers themselves are actually prime. It does not necessarily have to be prime numbers to be relatively prime, although those are ways that would always be relatively prime if they were both prime numbers. But it does not necessarily have to be so to be relatively prime. All right, so let's go ahead and begin with example 1 here. And in example 1, they're taking a look at some fractions, and what they're asking us to do is to simplify. In other words, reduce the fractions all the way down to lowest terms or simplest terms. So we've got, in the first one, the fraction 16 out of 80. Now, some people like to take 2 out of a fraction, for instance. because it's always easy to take 2 out because we see both the numbers are even numbers. We know 2 is going to come out. But the idea that they're presenting to you here is reducing the fraction with just one attempt. All right, and you can already see what we're going to divide by, but what you need to see is how we're going to get there. There's a couple different ways you can do this, but we've already talked about the idea of greatest common factor when we talked about relatively prime. So what you're going to do is approach this problem with the concept of greatest common factor. Remember, what we do in greatest common factor is we start off and we list the factors of the numbers that we're working with. So in this case, that would be 16 and 80. So I'm going to go through and list the factors of 16. For some reason, that's coming up rather large, so let me adjust that in just a moment here. We're going to list the factors of 16. And remember, when we're talking about factors, we're talking about numbers that multiply together to make a given number. So, for instance, 1 and 16 are factors of 16 because 1 times 16 is 16. And 2 and 8 are factors of 16 because 2 times 8 is 16. And 4 and 4, and of course I only have to write that once, 4 times 4 is the other way that makes 16. For 80, the list is a little bit bigger, but still manageable. Not a fun problem, but manageable. 1 times 80 is going to make 80. And 2 and 40 are going to make 80. And 4 and 20 are going to make 80. And 5 and 16 are going to make 80. And 8 and 10 are going to make 80. And what you want to do at this point is spot the biggest number that's on both of the lists. Again, both of the lists. And that's very clearly 16. So what you're then going to do is divide 16 out of both the numerator and denominator that you're seeing here. And when you do that, 16 divided by 16 is 1, and 80 divided by 16 changes into 5, and the simplified fraction is 1/5. Now they're doing the same thing in this question, and I can present to you now a little bit of a shortcut on this that will save you probably some time, especially if you have to sit there and list the factors, the numbers, to figure out what you're reducing. Here we've got negative 18 over 29. Let's speak to the negative for a minute. You're not going to worry about the negative when you're going through the problem and reducing. When you're done, just make sure you stick a negative back in the front. What you would want to do if you want to try and shortcut this, and we already know what the answer is, so it's not much of a concern to us, but you're going to list the factors of just one of the numbers. And I would generally suggest you pick the smallest one. So I'm going to pick the 18. The factors of 18 are 1 and 18, and 2 and 9, and 3 and 6. And then what you're going to do is just simply start dividing from the big end. Don't start at the small end because it's greatest common factor. You're going to do a lot more work potentially if you start at the small end. Start at the big end and start dividing. And whatever the biggest number that comes out of that other number, the number in the denominator is simply the greatest common factor. So I would do 29 divided by 18, but when I see that on my calculator, I see that doesn't spit out an integer, it's a decimal. 29 divided by 9, 29 divided by 6, 29 divided by 3, 29 divided by 2, and 29 divided by, not 29 divided by 1, but 29 divided by 2, all present the same issue. 2, 3, 6, 9, and 18, when I divide each one of those by 29, it spits out a decimal on the calculator. And of course, that's not where we're going to go with the fraction here. Dividing by 1 will, of course, leave the number the same, and it happens that that is actually the greatest common factor of 18 and 29. So dividing by 1 means that the fraction is actually already, in simplest form, already reduced. And furthermore, going back to the concept of our definitions here, that 18 and 29 are relatively prime. But again, that shortcut method will work even if it's a problem that we had to do. If we look back, a problem we had to do like question A, we could have just done the factors of 16 and started dividing. Well, when I did 80 divided by 16, we know right away that that's how we went to 5, and we would have stopped right away without ever having to make this list here for 80. The shortcut is optional. If you want to list the factors for both numbers, that you're certainly more than welcome to. It will, of course, get you to the correct answer. In question number 2, they're asking us to write the decimal as a fraction in simplest form. Now, what they've done here is they've written it as a mixed number, which is not an issue. It does not necessarily have to be a mixed number. It could be an improper fraction. Remember, an improper fraction is simply when the numerator is bigger than the denominator. There's nothing wrong with having an improper fraction, but let's say it became something like 200 over 100. That was something we could then reduce just like we did a moment ago. So what we're going to do here to write the decimal, I'll show you both approaches here. As a mixed number, let's ignore the part in front of the decimal for just a moment. This is 0.37. What you need to do is identify the place value of the last digit, which is 7. 7 is in the hundredths place. And that means the denominator of my fraction when I write it is going to be 100. The numerator is simply what we have there without the point. So if I erase the point, I just have 37. And that's what we're going to place in the numerator. And that's 37 over 100. As far as the 5 that's in front of the decimal, well, we just do the same thing. We leave it in front, but now it's in front of the fraction part instead of the decimal. And that's how we end up with 5 and 37 100ths. If you wanted to write this as an improper fraction, that's really not challenging at all. Again, you would do the same thing. Identify the place value of the last digit, 7, which is still in the hundredths place, of course. And the numerator is simply this number without the point. So now it's 537 over 100. Of course, you can check my math if you'd like, but 537 over 100 and 5 and 37 100ths are equivalent in that they both yield 5.37. So the answer is not different from one to the other. It's just a different way of expressing them. They both equal 5.37. Now, here is 0.622, and we don't have to worry about which way to go here because it's not presented to us with anything in front of the decimal, so we can jump right into the work here. Again, I want to ignore this part in the front and identify the place value of the last digit, which is the 2. This last 2 is in the thousandths place, so the denominator of my fraction is going to be 1,000. The numerator of my fraction is, again, this without the point. So it's going to be 622, and that's 622 over 1,000. Now that's all well and good. We do have a fraction there, but remember the directions did imply simplest form. And so here you would then have to reduce out the greatest common factor. Luckily for us, the greatest common factor here is just 2. So I'm going to divide 2 out of both the numerator and the denominator, and that's how I end up with 311 over 500. Okay, we'll continue with the next example, which is now asking us to write the fraction as a decimal. Now, writing a fraction as a decimal is perhaps a little bit simpler, probably made even simpler by the fact that you will use a calculator to do this most likely. When you're changing a fraction into a decimal, you're going to divide. You're going to divide the numerator by the denominator, or the top number by the bottom number. That's how this works. Don't try and do small divided by big, because that's not what we're going to do here to make this work every time. Go with numerator divided by denominator. It might happen to be the small number divided by the big number, as in B, but that doesn't always work, as you're seeing in A, because the big number is not in the denominator, it's in the numerator. So again, do numerator divided by denominator, top number divided by the bottom number. And again, these are great calculator problems. So in the A example there, you're going to do 11 divided by 9 on the calculator, and what you're going to see on the screen is 1, a decimal point, and then a bunch of 2's. That implies that that 2 is repeating. And you indicate repeating by writing a bar over the number, and that's why we have 1.2 with a bar over it. Again, this bar indicates that this 2 on the screen, when you calculate it, goes on forever, or it shows up through the end of the screen limits. One thing to note on some calculators, let's say the result was something like 1.6 repeating. on a calculator screen, this will appear as 1.6666, as many sixes as it can fill, but then the last digit will become a 7. The reason the calculator does that is so it knows to, at some point, to end the calculation. It's actually rounding that last digit. That does not mean that the answer is 1.6 repeating and then a 7. It simply means that the answer is 1.6666. All right, we'll look at B now, 7/20. 7 divided by 20 yields 0.35 on a calculator, and that is a terminating decimal, implying that it does not go forever on the screen, and that is simply the answer, 0.35.